Good morning, everyone. Myself, Rekha DN, from the Department of Allied Science, Physics Department, from RLJIT. So today I am going to explaining the topic that is Hall effect. So before going to see this Hall effect, so I will first explain some small introduction of about this Hall effect, how it's work and what principle it is work. Let us see. So now see here. So in this Hall effect, before going to see this, so any material if you consider, so any material if you consider all that material, if you apply an electrical energy like this, electrical energy to apply, just I am applying I am connecting a battery. So this battery whenever you connect, so we know that the charges will flow. In another words, we can say that the current will flow in this conductor. So when the current is flowing in this conductor, this indicates that the electrons are entering inside the conductor and electrons flow easily in this conductor. So that is the case. So we are saying that so the current is flowing in the conductor. So if there is no objections, if there is no opposition for the flow of charges, then the electrons will flow easily in this conductor. So in this circuit. But in the Hall effect, what is happening means, so whenever you connect, so in the Hall effect, sometimes we will take conductor, so our semiconductor also we will take. So imagine that I taken the N-type semiconductor. Any type semiconductor you can take. So I am considering an N-type semiconductor. So in this semiconductor, the which type of shape it is consists of means, so it consists of a rectangular shape like this. So this rectangular shape slab what I am considering, it is an N-type semiconductor. N-type semiconductor. So now see here, in this one, now I am applying an electric current by connecting a battery. Whenever you connect a battery, I told you as initial, that is the current is flow in the conductor. So in another words, we can say that the charges are flowing in the conductor. So it is a semiconductor. Now, when the charges are flowing in the conductor, suddenly I have to stop that. So for that reason, what I am doing means, so just I am connecting, one second. So now just I am connecting or I'm applying a magnetic field across this conductor. Whenever we connect a magnet or an apply a magnetic field perpendicular to this current, then the flow of charges what we are seeing in the conductor, it will stops and it will going to stay near at the top of the north pole or at the top of the slab. So that means all the electrons will stay in the upper slab of the upper side of the slab, and the remaining the electrons whatever we have all will flow again, the electrons will flow. So whenever the electrons will flow, so due to the flow of charges after applying a magnetic field, so we are seeing that so perpendicular to both this magnetic field and the applied current, there is a one more potential is existing. So our EMF is existing. So that EMF we are calling as a potential difference. So in our topic we are calling that as a Hall potential. So now I am explaining the definition of the Hall effect. Hall effect means whenever a current carrying conductor is placed in a magnetic field, the potential is induced in that conductor. So the definition you can say for this, a current carrying conductor is placed in a magnetic field, is placed in a magnetic field, a potential is An electric potential is induced perpendicular to the both magnetic field and an electric field. So this is Hall effect. So now we are known what is mean by Hall effect. So we are seeing that in this one, in this Hall effect, so we are seeing both the current turn and the magnetic field. So this is the applied magnetic field. Both are perpendicular to each other, and perpendicular to this, due to this applied magnetic field, we are seeing that one more potential or one more EMF is inducing. So that is perpendicular to both the current and the magnetic field, that is Hall voltage, Hall potential. So this how we can explain means we have the left hand rule, that is Fleming's left hand rule. So in this left hand rule, so the first three finger what we are considering all are mutually perpendicular to each other. So like that, so here also the magnetic field and the current and the induced potential are three are mutually perpendicular to each other. So after knowing this, so here in this explanation, so we have to derive an expression for this Hall potential. To derive this Hall potential derivation, so what I am considering means I am considering a two kinds of forces are existing. One force is due to the magnetic field. So that is we are calling as a Lorentz force. That force is equal to minus BE into VD. So this is applied magnetic field and the number of charge flows in the conductor, and next this is the drift velocity. So we know that, so according to the second assumption of an electroconductivity, so what we are seeing means the free electron theory is explaining that, so any conductor when you apply a magnetic field or electric field, any energy if you apply, so there if the electric field is goes on increases or the energy is increasing, then the velocity of the electron will also increases. Based on that concept, here, so whenever the applied magnetic field goes on increases, then the drift velocity will also increases. One more force is existing. So that force is due to an applied current, an applied voltage. So that is equal to, that is minus E into EH, where this is an applied Hall electric field. So both these two forces what I am considering, both are equal to each other. So that is equal to, if FL is equal to FH, then you can equate these two equations. So that is minus BEVD is equal to minus EEH. So now see here in this term, so the term electron, charge of an electron will cancel each other. What is the remaining is there means that is EH is equal to B into VD, that is drift velocity. Now see here the negative signs will cancel each other, that I am skipping here. So remaining things I am writing here, whatever is remaining that I have written here, that is Hall electric field, applied electric field. So now after considering this, so we know that this applied electric field is equal to the Hall potential by the distance between that upper slab and the lower slab, upper surface and the lower surface. The rectangular slab has a distance, say that is small d. So that distance I am considering VH is equal to VH by small d. So you have to keep in your mind that EH means applied Hall electric field, VH means Hall voltage or Hall potential, and the small d it is we are calling as a the distance of the slab between the upper surface and the lower surface. So after studying this, so here we have this VH is equal to, so what is that VH means? So VH is equal to EH into D we have. So here we have a EH term, that is B into VD. So VD means, that is already we know that is drift velocity. So drift velocity when it will exist means when you apply a electric field or any energy for a conductor, drift velocity will going to increases for all type of conductor. So we are applied an electric field or energy, due to this the drift velocity is existing. So after considering this expression, next see here, so we have to define the term. So here we define it, the magnetic field we have defined it, and this term we are defined it. In all this term, we are not taken this current term. Due to that reason, I am considering here the current density. What is mean by current density? Current density is the ratio of current by and unit area. So now see here, the current what I am defining, I can define with respect to the drift velocity. So that is I is equal to NEA into VD. So this is the definition for the current. So here if you take VD is equal to, that is I divided by NEA. So now see here, so this term I am putting this as a box, and here we can substitute the A term, that is area of the rectangular slab what we are considering. So to define this area, so that is the thickness we have to consider. The thickness of this slab I am denoting as a W, and this is the distance between the upper surface and the lower surface, that is small d. So we can take the area as the thickness of the slab and the distance between the upper surface and the lower surface. So substitute this value in this above equation. So you will get, that is VD is equal to I divided by NE A place only we have to substitute W into D. So this is VD. So now just substitute this VD term in this given equation. So you will get, so we got that VH is equal to BVD into BVD into D. So, and we got VD is equal to, I told you that the drift velocity it is. So, this drift velocity is equal to I divided by NE A. So now, so substitute this value in this equation, that is VH is equal to VD substitute value of this VD I am substituting I divided by NEA into D. So we know that A is equal to W into D, that is thickness, and the this distance between the upper surface and the lower surface. Substitute this A value, you will get B into I divided by NEA W into D into D. So D will cancel each other. So therefore VH is equal to D into I divided by NEW. So this is an expression for our the induced EMF existing perpendicular to both the current and the applied magnetic field. So this is the derivation. Thank you.